DecisionCAMP, and our first presenter is Peter Voss, and Peter is a well-known scientist in the artificial intelligence area. He devoted his whole life to what he called the mission to bring human-level AI to the world, and he actually he created company. He did all his life activities and real development in this area. Peter was among few people who started the name, who coined the term AGI, and Peter presented several times at DecisionCAMP, and it's always one of the most interesting presentations. And today in the world that dominates with the hype around generative AI, it would be especially to see I would say alternative or complementary development that goes beyond LLMs today. And Peter, thank you very much for joining us, and please take over.
Yes, well, thank you. And well, good morning, good afternoon, wherever you are. I'm going to be covering four sections. The first one is what is AGI, because there is a lot of confusion about that. The second one is why large language models are not likely to get us to AGI. The third section is what I believe the viable alternative is that we've been working on for some time. And the final section is basically specifically the progress we've made over the last year or so, that we've been focusing on cranking up the intelligence of our system. So the beginning parts will be similar to what I presented last year, but I think it'll be either a reminder for those who've seen it before or those who haven't seen it before. I think it's essential background. So what is AGI? Artificial general intelligence is the ultimate goal of AI. When AI, the term was coined 70 years ago, it was about building thinking machines that can think, learn, and reason the way humans do, so that they have the adaptability and intelligence of humans and can really learn anything. And this is why in 2002, three of us coined the term artificial general intelligence to get back to the original dream of AI, which is a system that can truly learn by itself. So it's autonomous and adaptive. Whereas almost all of the work that's actually being done in the field of AI is narrow AI, where you pick one particular problem that requires human level intelligence, and then you figure out how to write a program to solve that problem. So IBM's Deep Blue chess champion would be an example of that. But pretty much all AI, even current generative AI, it's how can the system have a good conversation or be a good agent, and then it's fine-tuned with a lot of human interaction to do that job well, and continues to require human intelligence. So AGI, in contrast, is really about a system that can adapt and learn by itself autonomously. And of course, having AGI ultimately is the big goal, and it'll be worth trillions of dollars because of all the benefits that are given. I'll talk about that next. So imagine a system where you can have 1 million AI level researchers. So take, for example, you have one system that teaches itself, that learns to become a PhD level cancer researcher. It'll hit the books and learn basically like a human, except much faster. To become a cancer researcher, now you can make 1 million copies of that, and you have 1 million PhD level cancer researchers that can pursue, different paths, different ideas at the same time, and share information. And you can apply that to basically every endeavor in science, and I'll cover some of those areas in a bit. Secondly, of course, it will dramatically reduce the cost of goods and services as we can automate more and more. And thirdly, which I think is really exciting for people to see, is to have AI, to have an AI that's what we call a personal assistant, where you have this superhuman level AI that you own, that serves your purpose, not some mega corporations, and that can basically help you think things through and get things done. So it's almost like an extension to your brain, an exo cortex. Now, now for some reason the previous slide didn't come up properly. So of course, computers, even at human level, still have several advantages over humans, and that they much lower cost than humans potentially. They communicate. They can share information much more easily. They don't have egos getting in the way. They can easily transfer information that one agent learned versus to another one. They can work 24/7 without getting tired, and even at a higher, faster rate. They don't have these nice distractions that we tend to have, like boys and girls. And of course, they have photographic memory. They have instantaneous access to all the world's information, whatever's on the internet, and they are much better at logical thinking than we are. For humans, logical thought is actually an evolutionary afterthought. We're actually not very good at that. So, that so AGI is just incredibly powerful. Now, just to contrast that, Sam Altman, this is a little bit older, but there's a lot of confusion in how people use the term AGI in order to raise money or to generate hype or whatever. There's a lot of confusion. So one of the things that, for example, Sam Altman said, oh, we'll have AGI soon, but it's not going to be a big deal. That's not AGI. So generally, of course, I have a very positive view of AGI. I don't believe there's any good evidence that AGI will be detrimental to humanity, but that's of course a whole another discussion. In fact, I believe AGI will help humans flourish. So just to very quickly, I don't want to take too much time on it, but how AGI will help advance quantum computers and just generally make computers themselves much more powerful in energy to finally have fusion energy, which is a really difficult technical problem, and better batteries and just clean energy. These are difficult technical problems that having AGI can dramatically accelerate development. Nanotechnology, we've been hoping to get nanotechnology for decades now, where we can have,
Peter, we don't hear you.
Yeah.
Okay.
Am I back?
Yeah, you're back.
Yeah. And to have, much stronger materials and so on. On the medical side, of course, to help really conquer disease, all sorts of different advances, again, that require a lot of brain power, a lot of intelligence to solve. Having better food that tastes good but is also healthy, just a lot of different benefits. And then on the philosophy and psychology side, AGI will help us figure things out. For example, we're not very good at the moment at figuring out how to govern ourselves. So by having better philosophy and ethics and being able to think through what are the kind of systems and what are the personal kind of rules that we should should live by, that'll help us flourish. I believe that's a very important area in which AGI can actually help us to have ethics that is more rational. And then on the psychology side, imagine each person having their own personal psychologist and advisor that can basically help them think through and flourish. So, you know, as you say, I believe AGI will be tremendously valuable and beneficial for humanity. So how do we get there? So in some sense, we seem to be so close. I mean, when ChatGPT came out and the advances we've seen now in you know, image and video generation, in some ways we seem to be so close to actually having AGI. But then on other, you know, once you scratch on the surface and you actually try to implement them and use them robustly and use them autonomously, very quickly realize that we still seem to be a long way away from that with the current technology that we have. And there are a number of problems. I mean, cost is one of them. You know, because they require such an enormous amount of computational power. Up to now, scaling has really advanced, but it's now exponential. Basically, 10 times bigger training cost. You know, doesn't give you 10 times better performance. So there definitely seems to be a leveling off and a plateau, and you know, exponential increases in cost when people are talking about you know, trillions of dollars. Like Sam Altman, we need $7 trillion to get to AGI. It's just, you know, where's that money going to come from, and you know, where's the equipment, the chips, and that are going to come from, and does it even make commercial sense? So you know, recently with ChatGPT 5. More and more people are saying that there is a wall, you know, I mean, not a solid wall as such, but that progress is dramatically slowing down in spite of the dramatic increases in investments that has been made. And also it's becoming clearer that, you know, hallucinations aren't going away, and that really just rearranging and, you know, orchestrating smaller agents that can work together that are more specialized. Brute forcing, just building bigger models, is definitely seems to be hitting a wall. And you know, it's not just my opinion. It's you know, leaders in the field. In fact, Jan LeCun puts it very strongly. He says large language models are an off-ramp to AGI, a distraction, a dead end. In fact, he tells his students not even to bother studying generative AI, because he believes that's not the path. And I agree with him. But even people like Demis Hassabis say deep learning, machine learning, generative AI are not going to get us there by itself. We need, not by a long shot, in fact. So, you know, this actually, when you talk to honestly, or more honestly, to technical people, there's actually agreement there. Now, there isn't agreement as to what will get us to AGI. Now, you know, real-time learning and memory is critical for AGI. That is something that I've only seen really coming up in the last few weeks or few months, where leaders in the field are starting to pinpoint what the big problem is. And the big problem is that these systems don't really have memory that's part of it. They cannot learn by themselves. So, you know, here's some choice quotes again from leaders in the industry, and there are links to it. You know, it's coming from you know, several sources that they're talking about that. But there really isn't a solution to that, because large language models, the core model itself, simply cannot be updated in real time. It cannot change its weight incrementally. You can put external rags, or you can have a bigger context window, but that does not change the actual weights in the model. So the model, you have to throw it away and train a new model, and then it's again frozen in time. And that's really not fixable. I have a white paper that I co-authored where we reviewed more than 200 recent research papers on this topic of trying to get large language models to learn incrementally. And there's not a single paper that has that actually has an answer to that, because really with backpropagation, it's not possible. You have to have all of your training data up front and then number crunch it. And really the best you can do is fine tuning at the edges. And even that is a bulk process. So these limitations really are not fixable. Hallucinations, there are lots of papers coming out saying that they're inherent in the way large language models use. You can reduce it to some extent, but then you lose some the power. So there's a trade-off, but you cannot actually get rid of them. The fact that they're black boxes is a problem. Limited understanding and no metacognition. They don't know what they don't know. They cannot really control like humans. We have metacognition. We have system 1, system 2. Our automatic sort of subconscious operation of the mind. And then we have the conscious supervisory metacognition that we have. And large language models don't have that kind of architecture. So, external guardrails that you can put to try and mitigate some of these problems. It's really, eventually it ends up being like the tail wagging the dog. You have all of these external systems, and to try and constrain what the large language models and then you ask yourself, well, did you actually need the large language model for a particular application, or could you just have used Google Dialogflow or some other robust existing technology to do the task? Now, let me just kind of interrupt here, because I've been talking about all of the limitations of large language models. Of course, there are many very valuable applications for large language models. I mean, I'm sure all of you are using them. I have like 2 friends of mine have recently written books, and the research they did, they say it's cut the time of actually coming up with a book. The book isn't written by large language models, but they're using the tools, and it's cut the time from 18 months to 2 or 3 months to actually write a book, and it's much better researched. There are obviously a host of different applications with generative AI that are really extremely worthwhile and powerful. But what I'm contrasting it with is the ultimate goal of AGI, autonomous adaptive intelligence that you can trust. And for that, I'm not going to go through that because I've already spoken about quite a few of these things. But if somebody's interested, I sort of stood back and said, well, why aren't we getting to AGI? And probably the key point is the last one on the slide is there isn't a robust theory of intelligence that people apply. They just say, hey, we've got a lot of data, we've got a lot of compute. What can we do with that? And we can do magical things with it, but it's not going back to first principles and saying, what is really unique about and important about human intelligence? What makes human intelligence so special? That's a first principle approach where you really start with the theory, and basically the field of LLMs doesn't have that. Even somebody as successful as Demis Hassabis, in an interview, he said that we don't understand intelligence. We have to build AGI in order to understand intelligence. Now, that to me seems really, upside down. If you want to build a system that has human-like intelligence, the power of human intelligence, maybe your starting point should be to understand intelligence in order to build it. So the lack of theory, I think, is really hampering AGI development. So the system needs to be both adaptive and autonomous. what's the solution? How can we something that doesn't cost 7 trillion, that, it costs a small, tiny fraction of that, can learn incrementally, doesn't hallucinate, and is auditable. And the approach is basically what we call cognitive AI. DARPA calls it the third wave of AI. It doesn't use back propagation. It's a knowledge graph, and it's based on small data incremental learning. So DARPA came up with this interesting model a few years ago that they call the 3 waves of AI. And the first wave of AI is, what we now call good old-fashioned AI. The second wave is hit us like a tsunami. That's the one we're surfing right now. Everything to do with statistical systems, big data, big compute. But the third wave is basically systems that are truly adaptive, and that is, cognitive AI, or we call it cognitive AI. I think is a good description of that. So, as I said, it starts with the question of what makes human intelligence so special, and what some of these key things are. It's adaptive. Its concept formation is a key part of it, that we are able to conceptualize. We are exposed to different examples of it, and we can then generalize. We can form abstract concepts, and we can form concepts on top of concepts on top of concepts. So the ability to form abstract concepts on the fly that are also contextual, that can change depending on the context, that is really key to it. And then, as I mentioned, metacognition, the ability to reflect on our own thinking, to reflect on our thought processes. So generative AI focuses on knowledge and skills. It has, these systems that are trained with 30 trillion pieces of information obviously have much more knowledge and skills in some way than any human will have. 30 trillion pieces of information obviously have a lot. It's way off the charts compared to what the knowledge that a human has. But they lack the real-time autonomous adaptive conceptual learning and operation. So that is the path to AGI. And so comparing these two approaches is really like chalk and cheese. The one focused on having knowledge, the other one is on the ability to acquire knowledge. I've already really covered all of these other things. This is just a summary. So again, one of the key issues is the ability to learn incrementally, so that you have a set of learning algorithms, what I've shown on the right there. And those learning algorithms allow you to acquire new skills and new knowledge. Now, there are tremendous advantages in having the ability to learn incrementally in real time. You literally require a million times less training data. Instead of 30 trillion pieces of information, you might have a few million. A child can learn language and reasoning with a few million words. And of course, the other thing is that comes with that, it requires a lot less computational power. So, our brain uses 20 watts, not 20 gigawatts. It doesn't need a nuclear power station. And once you have a system that can learn with much less data, you can focus on the quality of the data instead of the quantity. And that, of course, also improves the whole reliability, and it it can correct its mistakes and so on. It can run on a local machine, or even on a smartphone potentially, or on we run our systems on off-the-shelf computers, and so it provides all of these benefits. Just really that ability to learn incrementally. So yeah, to get to AGI, it's not going to help building bigger ladders. It's not going to get us to the moon. We really need a rocket. So third wave is that neuro-symbolic, because people like Gary Marcus have been beating the drum about we need Neuro-Symbolic. Now, a lot of people that talk about Neuro-Symbolic as being the answer really think about it as taking a logic system and just adding that to LLMs. So can you just kind of combine them, the two? And my argument is no, that's really not going to solve the problem. There are a number of reasons. One of them is you really need a common knowledge substrate. So your knowledge and skills that the system has need to be available to both the sort of pattern matching type, neuro type operations, as well as your logical operations. The updates need to happen together. So unless you have a common substrate, uh, adding an external symbolic system to a neural network or to a large language model is in a way going to give you the worst of both worlds. You're going to have the brittleness of the symbolic system potentially, and hallucinations and inability to update in real time. So while it can solve certain problems, and there are certain applications that are successful where people have added external, rule-based systems, logic systems to large language models, and then working together, certainly can improve it, but it's not going to give you the kind of um, capabilities that you need for AGI. So our approach is basically what we call INSA, integrated neuro-symbolic architecture. And the big difference here is that the knowledge representation is common for both the sort of neuro operation and symbolic operation. So all the knowledge and skills are represented by very high performance, a super high performance vector graph database. So it has both the ability to represent vectors and the advantages you have with sort of fuzzy matching of vectors, but it also has the graph structure that you can traverse and do logic operations on. In fact, the two can be used interchangeably. And I say super high performance. We've developed this from the ground up specifically for our system, and it is literally, we benchmarked it, it's literally 1,000 times faster than any commercially available graph database because it's been designed for that. And then all of the cognitive algorithms that are necessary are deeply embedded and integrated with this vector graph database. And that is how we actually get everything to work. Now, traditional cognitive architectures tend to be very modular. So, you might have a what's a good parser? Well, we'll use a Stanford parser, and then what's a good logic engine? Somebody's logic engine. What's a good knowledge database or graph database? And these things aren't integrated, and you have tremendous problems in them actually working together. And that's really one of the reasons why traditional cognitive architectures haven't taken over, because they're not integrated, apart from obviously some other specific limitations. So let me talk a little bit more about the sort of cognition, and then talk about what we're doing now. So as I mentioned, I believe concept formation is key to human intelligence. So we have inputs things we perceive through our senses, and then we learn what we experience. We can remember that and use it, but more importantly, we can generalize it, and we can then use that to make predictions and anticipate things, and also give us context. So there are these levels of abstraction that we have, and this is just a super simplified diagram, of seeing a dog and hearing it, and then being able to generalize those perceptions. Then you might see something that looks similar, but it doesn't bark, it meows, so that goes into a different category, and that's a cat. And that's really how children initially separate out these concepts. In addition to that, of course, what makes humans special is that we have language, so we can now label these concepts and then operate on these concepts through labels, and that's what what gives the language the ability to very rapidly call up different concepts without having to perceive them. And then through language structure, you can organize your thoughts and achieve high-level reasoning. So cognitive and learning mechanisms that we have, and of course to go through that would by itself, when we do this internally with new employees or something, go through that, that by itself is a multi-hour discussion to go through it. But I just want to kind of give a taste of how we actually do it. So we have these low-level cognitive algorithms, cognitive and learning algorithms, which are really pattern learning, pattern generalization, and pattern prediction system. Have kind of learning aspects and so on. So they are not specialized high-level algorithms that you might have in traditional programming. And then the graph structure again have to go into some take quite a bit of time to go into the detail. But these are the different kinds of things that are stored in a vector graph database. Both the input, once the features have been extracted from your input sensors, the instances and the generalizations, the relationships, the attributes that you have, action sequences, and the different kind of relationships and reinforcement links that are actually encoded. Even the metacognitive signals, like emotional things, confusion, and so on, they are also represented in this knowledge graph substrate. So the way we're going about building an AGI, over the last 20 years, I've alternated between developing a core technology, AGI technology, and then commercializing whatever technology we developed, went back to developing it further, commercializing it again, and we are now actually back to a development phase. Now, the problem with commercialization is, to run a commercial company, as you probably know, is a full-time job. It's non-trivial to just get customers and keep the lights on and grow. So when we're in a commercial phase, we didn't really have the ability to move the core technology forward. It was always, in fact, we kind of went backwards because you end up taking a lot of the adaptive aspects out of it. And I'll talk a little bit more about that later. And really all your time is spent in getting customers and scalability, redundancy, security, specific customer requirements, integration, and so on. And very little time is actually then spent on trying to improve the core AGI technology. So what you really need to do is to build a system that can learn by itself like a child. So that's what we're doing now, is we're teaching the system from the ground up language and reasoning ability. And that's what I'll show in the final section of the presentation. So the idea is to have something that lives on your PC. It can see everything that's on the screen, sense a mouse and keyboard, and control the mouse and keyboard. And so, which basically means, in principle, if it's smart enough, it can do any remote job, any desk-bound job. Could potentially control robots, of course, and machines, and so on. So anything you can control through that. That's the development path that you have. Now, once you have that kind of brain, you could, of course, put it into a robot as well, and and as supervisor of a robot. So what we would we call this kind of seed AI because as the system progresses, it needs less and less of a teacher. It can learn more and more by itself. And a child at 3 or 4, 5-year-old needs a lot of instruction, needs a lot of supervision. But then once you get to 7, 8, 9, 10-year-old, you can hit the books by yourself. And most of the learning is then sort of can be self-motivated and knowing when to ask a teacher for help or where to get help. So by the time you get to 10-year-old, you can be actually very much autonomous as a learner. So whether it's 10-year-old or so is debatable. But that's basically the approach. And then the other thing I'd just like to point out when people say, well, don't you need all of the sensors? Don't you need robotics in order to get AGI? So, and I call the system, I call this the Helen Hawking theory of AGI. And what I mean by that is Helen Keller and Stephen Hawking. Helen Keller had very limited sense acuity. Stephen Hawking had very limited dexterity. And of course, they were both very, very smart. So the idea is that you can have a super smart system that has limited sense acuity and limited dexterity. And of course, we can see that in some ways with large language models. So once you have the intelligence, you can then focus on adding additional sensors and dexterity. So what I mentioned in switching between having development companies and commercial companies, one of the things I've seen pretty consistently, and we've certainly experienced it and fallen into this narrow AI trap with our eyes open, is that as soon as you try to beat a particular benchmark or have a commercial product that you're going out on, or even doing a demo to get funding, you invariably use human intelligence to hard code a bunch of stuff or to specifically design something to beat that benchmark, or even publishing a paper you want to show something specific, impressive, to do a product. So you basically then veer off the development that needs to be done to actually get to AGI, to focus on the learning mechanisms. Because the initial learning mechanisms, learning of a 3 or 4-year-old is not very impressive. It's not going to beat any benchmarks. So you really have to stick to the theory of what is important to develop, and not what benchmark can I beat or what product can I get on the market. It's really very, very hard to stick to this AGI development and not fall into that narrow AI trap. So on the commercial side, for example, and this is a concrete reflection of it, we had a lot of handcrafted rules for language, for reasoning, for business rules, and so on. For example, one of our commercial customers, 1-800-Flowers, Harry David group of companies, paid us $400,000 to set up the system for them, to build the ontologies and business rules and so on. So there's a lot of human labor that went in to do that, but that's not AGI, that aspect of it. AGI would be like you or I going to the call center at 1-800-Flowers. We read the manuals, listen to some calls, ask a few questions, and then we can take customer calls, because we can learn and we can adapt. We know when to ask questions, when to hand off to a supervisor. We have that adaptability to learn on the fly. So the pure AGI development that we've been doing for the last year is we stripped out all of those handcrafted rules, and we basically built the system that it can learn by itself. So it has minimal code, only those core algorithms that I showed you. And then the rest of the system really needs to learn through a curriculum that we develop. I think in the interest of time, well, actually, I can just mention quickly. So the idea is to have a system that has the core knowledge, and then you can make a billion copies or billions of copies of that, and they can then learn by themselves to become expert in a particular area, in a particular company. They can learn that. And for personal assistant, you would have that third layer on the outside where it then becomes customized to you. So the blue layer might be the general knowledge you need for a personal assistant, but the green layer is the things that are specific to you. So the focus is on curriculum. Half of our company are actually not programmers. They are what I call AI psychologists. It's a profession I invented. So they typically have educational, linguistics, cognitive psychology background. They come up with a particular curriculum and the test to teach our system language and reasoning, and then to evaluate it. And then on the engineering side, we will then tweak the algorithms, improve the algorithms, the learning algorithms, generalization, prediction, and so on. So about late last year, we got to a point where we had roughly the cognitive ability, language and reasoning ability of a 3-year-old. We got to that milestone, and then a few months ago we got to roughly the ability of a 4-year-old. For the last few months we've been working now on getting to 5-year-old, which is already, as you will know from children, by the time you get to 5-year-old, you have theory of mind and you have actually very sophisticated cognitive abilities already. So that's the level we're working at now. I'll show you some examples here to wrap up. So, for example, this is the screenshot from our development system. So we will show it these different images, and then from perceptual cues, it might categorize them, or we might tell it like a child. You might point to something and say, well, this is a dog, this is a dog, this is a cat, this is a cat. And then by having a supervised learning, essentially you have a label and you say, well, what features are different? Well, dogs are a bit bigger, or you may have sound input, or hear what they sound like. So what the system is able to do is to both form concepts unsupervised through features and through supervised assistant where we would label them. And then it would also have the ability to disambiguate, or say this is ambiguous. What is this, a cat or is this a dog? Or something that looks different. Well, this is a rabbit. So it can recognize the instances, specific named instances, but also the categories. And it's the system is scrutable. Of course, once you millions of nodes with a lot of information, not trillions but millions, it gets very complicated. You can always identify how the system came to a certain conclusion, why it recognized something as what it is, or why it took a certain action by following it through. But you may need some pretty sophisticated tools to find your way through the vector knowledge graph. We also trained it where we have, in fact, these can be animated. We have people, walking, or you have critters that are jumping and things like that. So we're teaching it basically actions and verbs, like running, walking, jumping, and so on, and also relationships, that things are next to each other, on top, below, and above. So these are the core language abilities where you have entities that are nouns, you have attributes that are adjectives, and you have relationships, prepositions. And those are the core elements in verbs for actions. So we're teaching it while showing the system, so that you have this grounding, even though the grounding is quite primitive in current development. But you have these grounded concepts and the ability to learn language and reasoning. We then also, like a 4-year-old, we tell it bedtime stories. So we tell it a story and then ask questions about that. Yeah, you could read that if you have interest in it. You'll see a little bit more detail. Then we also have certain tasks are reinforcement learning. We don't believe that reinforcement learning is a major mechanism for learning, because it's actually quite inefficient. And humans actually don't learn a lot by reinforcement learning. I mean, you do, of course, by touching a stove and stuff like that. But reinforcement learning is, as I say, not a major modality, because it is just super inefficient. Once we get to 4-year-old, and some of the tests we do, we actually take off the internet. We find tests that they actually give to 4-year-olds, 5-year-olds, and so on. So this is a match to sample, where you show it the number of items and then say, well, which is the most similar or the least similar item to that, and we get our system to do tests of this nature. Piagetian categorization skills. In fact, I'm a bit surprised that they're for ages 7 to 11. I would have thought that be younger age, but we do tests of that nature as well, that we give out our system. Reading comprehension, I said we have bedtime stories, but we also, again, these are tests that are generally available and given to 4-year-olds, 5-year-old. And our system basically can learn how to answer these questions and do sentence completion and things like that. We've also started to teach it how to use tools. Basically, in this case, we're teaching it how to use paint or something similar, where it can select the color and then draw a line and combine these different lines and draw more elaborate shapes. And then now the current development that we're doing, sort of going towards 5-year-old, obviously these become more sophisticated. So again, if you're interested in some of the detail, these are kind of what we did at the 3-year-old level, what we're doing, what we did at the 4-year-old level. So to wrap up, I really believe we are a unique moment in history that on the one hand, ChatGPT shows us that in some ways we are so close to achieving AGI. You can, from an inference point of view, you can run a medium-sized language model, on an off-the-shelf computer. So it seems like there is enough hardware. Hardware by itself is probably not a limitation if you had the right software. And I think that's really the challenge, is to have the right design, to have the right software. And I believe we can get to AGI very quickly. I believe with our approach, I believe we are probably, with the right amount of funding, and I'm not talking about trillions or even billions of dollars. We believe we need another 50 people on our team for 2 years to get to adult level intelligence. But irrespective of whether my assessment is correct, I believe with the right software, you can have systems that need 1 million times less training data and a lot less computational power, and can get us to AGI within a few years. So imagine having this kind of system that can have million researchers or billions of researchers that can help us solve difficult problems, instead of spending trillions on these engagement machines that we have now for chat, with all the problems that they have by not being smart enough, to have technology that can truly help human flourishing. And I wish more people had that kind of mission to say, how can we have AGI that'll help human flourishing? And I invite any of you that have that motivation to contact us and see if we can get people together to motivate that happening. So I believe our company has what it takes. But irrespective, I believe that getting to AGI is really important and possible. Thank you.
Okay, thank you, Peter. It's, as usual, it's very promising and very enlightening presentation. At the same time, I personally got a feeling not very optimistic, because I don't hear that you can, we're not in the position when you can offer something that will attract not even to a general public, but to developers, that we can try and we can get this feeling right away. Certainly we can follow links from your presentation and try several suggestions, but I would let other people to ask questions. We have time for questions. Go ahead. Anybody?
Just one question, and it's more technical than positioning. I was very surprised to see that you had taken a vector database, graph database approach. Can you tell us a little bit about the motivation for this particular choice of graph, knowledge graph?
Well, I'm not sure what the alternatives are, but you know, a key requirement for human intelligence is concept formation and vector representation, not the kind of vector representation that you have in large language models where you have a fixed size vector and the vectors are generated through statistics. Our vectors are variable size that depend on what kind of concept you're trying to encompass. So vectors have, you know, are just powerful for pattern matching, basically for conceptualization. But you also need to be able to encode hierarchies and relationships and sequences, which you couldn't, you know, do in a graph database. So by combining, you know, nodes that are actually vectors in a graph database, it gives you an incredible flexibility, and that's really what allows us to have a true, what we believe is a true neuro-symbolic system, integrated neuro-symbolic. So I can't think of an alternative that would give you that kind of power. Now, by the way, I think we're just about out of time. It's very easy to get hold of me, and I'd welcome, you know, anybody to contact me on, you know, LinkedIn or X or wherever. You could just email me. You know, anybody who'd like to have more of a discussion, I'll be very happy to do that. I think we have time for another one or two questions, maybe.
Yeah, Kristen, go ahead.
Your presentation was fascinating and I learned so much. Thank you. I was really interested in your thought about the difference between early learning, where you're doing association, pattern recognition, cause and effect, and then that next leap to either a need or a curiosity driving humans or other animals to go look for new ideas, like Newton coming up with the idea of effect at a distance, right? So there's that difference between learning the world around you, seeing the cause and effect of things, learning other people's reactions or what happens scientifically, and then that mental leap to say, I'm going to think about things completely different. And I'm curious if you guys have thought through the difference between pattern learning versus the creation of new thought that's either driven by absolute desperate need or just pure scientific curiosity.
Right. Yeah, absolutely. So part of the metacognition are what you might think of as emotions or metacognitive signals. So one of those is curiosity that the system has. I believe you need things like surprise, curiosity, boredom, you know, and so on. They need to be metacognitive signals to drive the system. Now, in an AI, you can kind of tweak those much more. You can have much more control than humans. And imagination is also something where the system can basically trigger different concepts and kind of picture them in their minds, as it were, and use them. So yeah, absolutely, that is I believe essential for AGI.
We have time for another question. Okay. Peter, may I ask you, last year, during your presentation, you mentioned that, if I remember correctly, that only 3 commercial company is working in AGI direction. And I saw that now Meta and Jan LeCun in particular is developing something similar what you just described. And based on this development, do you expect that not general public, but at least we developers would be able to download and try some of results? When can it happen? In a year, in a 2?
Yeah. So we don't really have any plans to make this available until we reach 10-year-old level, at which point it'll be very rapidly commercially available. It's just, we don't really see the benefit of that. Now, I don't know what Jan LeCun, they did tend to open source things. His focus is still very much on, he doesn't have a neuro-symbolic approach really. And his goal is over the next quite a few years, he believes it'll take quite a few years to get more like to cat level intelligence. So his approach is much more heavily based on perception, which is not a bad approach. If you could truly get animal level intelligence, I think it wouldn't be that hard to then add the higher levels. But doing perceptual based development is just incredibly expensive, computationally and data expensive. And so he's still very much in the realm of big data statistical systems, which is actually interestingly aligns very much with what people are doing in robotics. In robotics, it's a lot of high dimensional data that you get. In robotics are doing reinforcement learning mainly to get it to do specific things, whereas I think Jan LeCun is more interested in taking this high dimensional perceptual data and kind of building world models from that. But his focus, as far as I know, is pretty much on sort of animal cognition. And I don't really know of any other company. Intel have a research program that does something that does cognitive AI. In fact, in their presentations, they borrow some of our slides. But it seems to be a small effort, and Intel, of course, has its back to the wall. So I don't know how much funding they actually have on that project. The other project that was similar was in a company, Elemental Cognition. Unfortunately, they've just closed their doors, so they're no longer working on that either. As I say, it's really hard to have that vision and to have the funding to continue down that AGI path and not fall into the narrow AI trap. I mean, what you're saying is, you'd like something you can download and play with. For us to produce it, we would end up going down the narrow AI trap again, because it has to be impressive, it has to be useful, and so on. So, it's really, you need to just get through that cognitive development to the point where the system, you've got all the cognitive systems in place, and the system really can then just learn by itself.
Okay. I hear you, and hopefully everybody can hear and appreciate all your, I would say, missionary activity right now. And we wish you to reach 6 years old level as soon as possible. And thank you very much again for enlightening presentation.
Yeah. All right. Well, thanks for having me again. And as you see, I'm still very enthusiastic about the project. So,
okay.
Thank you. And good
Thank
luck
you,
with
Peter.
the rest of the conference.
Thank you.